Hello there, and welcome to Life Beyond Seen, where curiosity drifts like a slow current, and science takes the long scenic path toward wonder. Tonight we're sinking far below the surface of the familiar into a realm that most of us will never lay eyes on, but that shapes our planet in profound and often surprising ways. It is a place without sunlight, where pressure could crush a submarine like a soda can, where temperatures hover near freezing, and where creatures exist that look as if they were dreamed up in the mind of a science fiction writer after too little sleep and too much coffee. It is the abyss, the deep ocean beyond the reach of a light, a realm so alien that it might as well be another planet hiding just beneath our feet. Before we dive, I'd love to know, where in the world are you listening from tonight? And have you ever wondered what might be swimming beneath the deepest part of the ocean near you? If this slow exploration of the strange and the unseen helps you unwind, or if you find a little calm in the idea that there's still so much mystery left on Earth, I'd be grateful if you'd like the video, maybe subscribe, and share this quiet curiosity with someone else who might need it. Now, take a breath, let the noise of the day fade a little, and imagine the surface of the sea stretching out before you, endless and blue, hiding beneath it one of the strangest worlds we know. The ocean covers more than 70% of our planet, and yet we've explored only a small fraction of it. Most of what lies beneath remains unseen, unvisited, and in many ways, unknown. The deeper we go, the stranger it gets. Just a few meters down, sunlight begins to dim. 100 meters, and the light is already weak. At 200 meters, you're entering the twilight zone, where the last scraps of sunlight filter through like pale ghosts. Beyond 1,000 meters, the light is gone completely. This is the midnight zone, a realm of perpetual darkness, where pressure climbs to hundreds of times what it is at the surface, and where the temperature barely creeps above freezing. Beyond that lies the abyssal plain, stretching for thousands of kilometers across the seafloor, and below even that, the Hadal Zone, the trenches that cut deep into the crust of the earth, where the pressure is so immense that metal hulls bend and even the toughest machines struggle to survive. It is in these places that evolution has written some of its strangest stories. To understand why the abyss harbours such bizarre life, we need to understand what it is like down there. Imagine a world without light. Not darkness like a moonless night where your eyes slowly adjust and faint outlines emerge. This is complete darkness, a permanent absence of sunlight. Plants cannot grow here because photosynthesis is impossible. Vision, at least the way most animals on the surface use it, is often useless. Instead, other senses take over. Creatures feel vibrations in the water, detect faint traces of chemicals drifting from distant prey, or glow with their own light to signal, to hunt, or to lure. The lack of sunlight is not just an absence, it is a force that shapes everything, from how creatures feed to how they reproduce to how they perceive the world. Now add pressure. With every 10 meters you descend, pressure increases by about 1 atmosphere, the weight of Earth's atmosphere at sea level. At the bottom of the Mariana Trench, nearly 11 kilometers down, the pressure is more than 1,000 times greater than what you feel at the surface. That's like having 50 jumbo jets balanced on a single square meter. Human bodies would be crushed instantly. Even steel hulls deform under such force. But life here is built differently. Cells are reinforced in subtle ways. Proteins have shapes that resist compression. Membranes stay flexible. Bones, if they exist at all, are reduced to lightweight scaffolds, or are replaced by soft tissues that bend rather than break. What would be lethal to surface dwellers is simply the background condition here, as ordinary as the weight of air is to you. It's not just darkness and pressure. The temperature of the deep sea hovers near freezing, often just 2 or 3 degrees Celsius. Food is scarce. Most of it drifts down from the surface. Tiny flakes of dead plankton, fish and fecal pellets, collectively called marine snow. This snow falls constantly but sparsely, a slow rain of nutrients that might take weeks or months to reach the abyss. In some places, carcasses of whales or large fish sink to the seafloor, becoming oases of life for years, but such events are rare. Most of the time, the deep sea is a desert of scarcity. In this desert, life cannot afford to waste energy. Every movement, every adaptation is a careful balance between cost and survival. When you put all of these conditions together, permanent darkness, crushing pressure, near freezing temperatures and relentless scarcity, you get a world that forces life into extraordinary forms. A creature that wants to survive here must either become a master of efficiency, a patient ambush predator, a scavenger willing to eat whatever drifts by, or a specialist in a niche so narrow that no one else competes. Over millions of years, evolution has tried every possible solution, and the results are astonishing. Consider the anglerfish, perhaps one of the most iconic residents of the deep. With a body that seems almost unfinished, a gaping mouth lined with needle-like teeth, and a lure that dangles from its head like a tiny lantern, it looks like something drawn from a nightmare. Yet every feature of this fish is a finely tuned adaptation. Its lure is a bioluminescent beacon, created by symbiotic bacteria that attracts prey in the darkness. Its huge mouth and expandable stomach allow it to swallow animals nearly as large as itself, a crucial skill in a place where meals are rare and unpredictable. Some species have reduced males to tiny parasitic partners that fuse to the bodies of females, an efficient if unsettling solution to the problem of finding a mate in the vast empty dark. Or take the gulper eel, whose enormous mouth can unhinge to engulf prey much larger than its narrow body suggests. In a world where meals may come once a month, the ability to eat whatever you can catch, regardless of size, is an evolutionary advantage. The barrel-leaf fish, with its transparent head and tubular eyes pointing upward, is another masterpiece of adaptation. Those strange eyes are designed to spot the faint silhouettes of prey above while the fish itself remains hidden below, and the transparent dome shields them from the stinging cells of siphonophores, colonial predators that drift like ghostly nets through the water. Many deep-sea creatures glow. Bioluminescence is so common here that some scientists estimate the majority of deep-sea species use it in some form. Some use light to lure prey, like the anglerfish. Others use it to attract mates or communicate. Some squid and shrimp release glowing clouds to confuse predators. Even predators use light as camouflage, producing a soft glow on their bellies that matches the faint light from above, making them nearly invisible from below. In the darkness of the abyss, light is language, weapon, disguise, and beacon all at once. Then there are the gelatinous drifters, jellies, comb jellies, siphonophores, that make up much of the biomass of the deep. These creatures seem almost alien, bodies composed mostly of water, transparent and delicate, pulsing through the dark in slow, graceful motions. Some siphonophores stretch for tens of meters, longer than blue whales, yet are colonies of many individual units working together. Others have evolved intricate lures that mimic prey to draw victims close. These drifting hunters remind us that in the abyss, softness can be a strength. Without rigid structures, they withstand pressure without breaking and conserve energy by drifting with the currents. Not all the abyss's inhabitants are delicate. The giant squid, once a creature of legend, lurks in the depths with eyes the size of dinner plates, adapted to detect the faintest glimmers of movement in the darkness. Its elusive cousin, the colossal squid, may be even larger, armed with hooks on its tentacles. These cephalopods are reminders that the abyss is not empty. It is a place where predator and prey engage in slow, silent battles far from human eyes. One of the strangest things about the abyss is how slowly life moves. With so little food and such low temperatures, metabolism slows to a crawl. Some deep-sea fish grow so slowly that they may live for centuries. The Greenland shark, which spends its life in cold, deep waters, is estimated to live up to 500 years. Even reproduction can be glacially slow. Some species take decades to reach maturity, and their populations recover very slowly from disturbance. This sluggish pace gives the abyss a timeless quality, as if the creatures here exist outside the hurried rhythms of the surface world. The scarcity of food has also led to some of the most extreme feeding strategies on Earth. Some deep-sea creatures are opportunistic scavengers, consuming anything that drifts their way. Others rely on ambush, waiting motionless for hours or days until prey comes within reach. Some, like certain deep-sea worms, feed on the bones of whale carcasses, extracting nutrients from what others cannot digest. And then there are the communities that have broken free from the need for sunlight altogether, around hydrothermal vents, where superheated water rich in chemicals gushes from the seafloor. Entire ecosystems thrive on chemosynthesis instead of photosynthesis. Bacteria here convert chemicals like hydrogen sulfide into energy, forming the base of a food web that supports giant tube worms, blind shrimp, and strange crabs. These vent communities are among the most alien ecosystems on Earth, thriving in conditions that would kill most surface life. This shift from light-based to chemical-based life is not just a curiosity. It tells us something profound about the nature of life itself. It shows that sunlight is not the only way to power ecosystems. Life is flexible, inventive, and stubborn. Give it energy in any form and it will find a way. It also suggests that if we are searching for life beyond Earth, we might do well to look not just for planets with sunlight, but for places with chemical energy. Icy moons with subsurface oceans, perhaps, or planets with volcanic activity beneath their crusts. The abyss teaches us that life does not need the familiar to flourish. The creatures of the deep are not just strange for the sake of strangeness. Each bizarre feature is a solution to a problem posed by the abyss. Transparency makes you invisible. Gigantic mouths let you seize rare opportunities. Glowing lures draw prey to you instead of forcing you to chase them. Reduced bones resist crushing pressure. Slow metabolism conserves precious energy. Even gigantism itself, seen in giant isopods and colossal squids, may be a response to the cold and scarcity, as larger bodies are more efficient at conserving heat and storing energy. And yet, for all its alien qualities, the abyss is part of our world. It influences the carbon cycle, stores vast amounts of heat, and drives global currents. It is a crucial part of Earth's climate system, a deep reservoir that moderates temperature and sequesters carbon for centuries. It is also a vast archive of evolutionary history. Many deep-sea species belong to lineages that have changed little for millions of years, relics of ancient oceans that predate the rise of mammals or even the breakup of continents. They are living windows into Earth's past, reminders that the deep sea is not just strange, but old. Exploring this world is difficult. The pressures are immense, the distance is vast, and the darkness total. Even our most advanced submersibles can only stay at great depth for limited times. Most of what we know about the abyss comes from brief glimpses, camera footage, samples hauled up on long cables, or remote vehicles peering into the dark. Every expedition reveals new species, new behaviours, new mysteries. We found fish with heads that act like windows, shrimp that farm bacteria on their bodies, worms that build feathery nets to trap food drifting by. And with every discovery, we are reminded of how little we truly know. The deep ocean is often described as Earth's final frontier, but perhaps that's not quite right. It's not a frontier waiting to be conquered. It is a vast, ancient realm that has existed for billions of years, shaping life in ways we're only beginning to understand. It is not empty, but teeming with life in forms that challenge our ideas of what life can be. It is not separate from us, but deeply connected to the planet we depend on, the oxygen we breathe, the climate we live in, the cycles that sustain life. All are influenced by what happens far below the waves. As we continue to descend into this realm in our imagination tonight, think about what it means that such a place exists here on Earth. a world as strange as any we might find on another planet, hiding beneath a surface we think we know, a place where darkness rules, where pressure shapes flesh and bone, where scarcity breeds invention, and where life thrives without sunlight. The Abyss is not an alien world. It is our world, one we have barely begun to understand, and the creatures that dwell there, however strange they may seem, are not outsiders. They are part of Earth's story, chapters written in darkness, pressure and patience. And so, we keep drifting downward, deeper into the story of this hidden realm, where the strangeness is not just a curiosity but a key to understanding life itself, where adaptation is art and survival is a slow, intricate dance played out in silence and shadow. The surface world may be bright and bustling, but below, in the endless dark, another world hums along, quietly shaping the planet above it. And that is where our journey will continue, as we look closer at how creatures in this realm not only survive but thrive in ways that defy everything we once thought possible. Imagine the moment when the last rays of sunlight fade away above you, swallowed by the dark water. Even before you've truly begun your descent, the familiar world is already slipping behind, replaced by something ancient and alien. A few meters below the surface, light begins to scatter and weaken. At 10 meters, reds and oranges vanish, leaving only shades of blue and green. At 100 meters, the light feels ghostly and pale, like twilight stretched thin. By 200, it is little more than a memory, and by the time you pass 1,000 meters, light is gone entirely. There is no dawn or dusk here, no cycle of day and night, no sun to rise or set. It is an unbroken, eternal night. This is the deep ocean, and it is a world defined as much by what it lacks as by what it holds. It's easy to underestimate what that absence means, because on land, light is so fundamental we barely notice it. Plants lean toward it. Our sleep and wake cycles are anchored to it. It shapes weather, seasons, migration, and the growth of entire ecosystems. Every breath you take is a gift from photosynthesis, a process powered by sunlight. But below a few hundred meters of ocean, that power simply doesn't exist. Without sunlight, there is no photosynthesis. Without photosynthesis, there are no green plants or algae forming the base of the food web. Life here cannot build itself from sunlight and air the way it does above. It must find another way. The first thing to understand about a world without sunlight is how profoundly it changes the rules of survival. On the surface, energy flows downward from the sun through plants and algae to herbivores and then to predators. In the deep sea, the chain is reversed. The rain of marine snow, tiny particles of dead plankton, fecal matter and organic debris, falls from above, carrying energy from the sunlit surface into the darkness. Most deep-sea creatures rely on this slow, steady snowfall. It is meagre, but it is life. A single flake of marine snow might take weeks to drift from the surface to the abyss, feeding countless small creatures along the way. By the time it reaches the deepest layers, much of its energy is gone, scavenged and recycled again and again. What's left is precious, and competition for it is fierce. This scarcity explains many of the strange features we see in deep-sea life. Big eyes are rare because vision is costly to maintain when there is nothing to see. Speed and constant motion, common in sunlit waters, would waste energy here. Instead, deep-sea creatures move slowly, conserving every calorie. Many are ambush predators, lying motionless for hours until prey drifts close enough to strike. Others have enormous mouths and expandable stomachs, allowing them to swallow prey much larger than themselves, a useful trait when meals are unpredictable and infrequent. Still others scavenge, following faint chemical trails through the water to reach a carcass before their competitors do. In a world without sunlight, energy is too precious to waste, and efficiency is the law of survival. darkness also changes how life senses and communicates. On the surface, vision dominates. Bright colours advertise warnings, attract mates, or mimic the environment. In the deep sea, sight often plays a minor role, and light itself becomes a rare and powerful tool. Bioluminescence, the ability to produce light through chemical reactions, is widespread here. Some creatures use it to lure prey, like the anglerfish with its glowing lure dangling just above its mouth. Others use it to communicate, flashing patterns of light to signal mates or warn predators. Some squid release clouds of glowing fluid to confuse attackers, much like an octopus's ink. Even camouflage can involve light. Certain fish produce faint glows on their undersides that match the dim light from above, erasing their silhouettes and rendering them nearly invisible to predators below. The absence of sunlight doesn't just shape bodies and behaviours, it reshapes entire ecosystems. Without light, plants and algae cannot anchor food chains, so most deep-sea communities depend on what drifts down from above. But there are exceptions, and they are among the most remarkable ecosystems on Earth. Around hydrothermal vents and cold seeps, where water rich in chemicals like hydrogen sulfide or methane gushes from the seafloor, life builds itself not on sunlight but on chemical energy. Bacteria here use chemosynthesis to convert chemicals into food, forming the base of a food web that supports giant tube worms, clams, crabs and shrimp. These communities are not dependent on the surface world at all. They exist in a closed loop, drawing energy from the Earth's interior rather than the sun. They thrive in complete darkness, proving that life does not need sunlight to flourish. Such ecosystems may seem like rare exceptions, but they reveal a deeper truth about life on Earth. Sunlight has shaped most of the biosphere, but it is not the only way to power it. Life is far more flexible than we once imagined. It adapts not just to the presence of energy, but to its absence, finding ways to survive where none should exist. That flexibility is why the abyss looks so alien. Every adaptation is a response to constraints we can barely imagine from the surface. Transparent bodies make animals nearly invisible. Gigantic eyes, when they exist, capture the faintest glimmers of bioluminescence. Enzymes and membranes evolve to function under crushing pressures. Predators develop jaws that can engulf prey half their size because the next meal might be weeks away. Each strange feature is a story about life adapting to darkness. Darkness also affects how time moves here. In the sunlit world, day and night structure life's rhythms. Plants open and close their leaves. Animals hunt, mate, and migrate according to the light. Even humans feel the pull of this cycle. Our bodies are tuned to a daily rhythm set by the rising and setting sun. In the abyss, that rhythm is gone. There is no sunrise or sunset, no seasonal change in light. Life follows other cues, the slow rain of food from above, the shifting currents, the rare arrival of a carcass. Some deep-sea species live for centuries, growing slowly in the cold, dark water. Others reproduce infrequently, their populations rising and falling over decades. Time in the abyss feels stretched, unhurried, almost geological. It is a realm where patience is not just a virtue but a necessity. The absence of light has another subtler effect. It blurs the boundaries between predator and prey, hunter and hunted. On the surface, sight defines these roles clearly. A lion sees a gazelle and gives chase. A hawk spots a mouse from above. In the deep, where vision is unreliable, life relies on deception. Many deep-sea predators are ambush hunters, relying on stillness and surprise. Others lure prey close with glowing bait or chemical signals. Some mimic harmless drifting debris until a curious fish ventures too near. Even prey species play this game, using bioluminescence to startle predators or slip away under cover of glowing clouds. In the dark, the line between danger and safety is never obvious, and the arms race between hunter and hunted is fought in silence and shadow. For us on the surface, light is often a symbol of life itself, and darkness is its absence. But the abyss shows that this is not always true. Life does not flee the dark. It reshapes itself to live there. It does not vanish under pressure. It bends and softens until pressure is ordinary. It does not starve in scarcity. It becomes frugal, patient, opportunistic. In many ways, the deep ocean is a mirror held up to life itself, showing us not just how it thrives when conditions are ideal, but how stubbornly it persists when they are not. The abyss is not empty because it lacks sunlight. It is full precisely because life found ways to make that absence irrelevant. This has implications beyond our own planet. If life can flourish in eternal darkness here, feeding on chemicals or drifting snow, why not elsewhere? Jupiter's moon Europa and Saturn's moon Enceladus both harbour oceans beneath icy crusts, cut off from sunlight, but possibly warmed by internal heat and rich in chemical energy. The vents and seeps of Earth's abyss may be the closest analogues we have to those alien seas. If we ever find life beyond Earth, it may look more like a tube worm clinging to a vent than a tree basking in sunlight. The deep ocean, far from being irrelevant to the search for life, may hold the key to understanding it. It is also worth noting that the absence of light doesn't mean the absence of change. Though it appears static and unchanging, the deep ocean is dynamic in its own slow way. Currents flow, sediments shift, and nutrients move along invisible highways. The rain of organic matter from above fluctuates with the seasons, with plankton blooms, with climate cycles. Even hydrothermal vents, those self-contained oases, are not eternal. They erupt, flourish, and die over decades, leaving behind ghostly chimneys while new ones spring to life elsewhere. Life follows these changes, colonizing new vents, adapting to new flows of food, shifting as the environment shifts. Darkness is constant, but within it the story is always moving. Humans have barely scratched the surface of this dark world. Most of what we know comes from brief expeditions, glimpses caught by remotely operated vehicles or deep-diving submersibles. Each dive reveals new species, new behaviours, new mysteries. We have found jellyfish that look like living chandeliers, fish with transparent heads, and creatures that produce light brighter than anything else in the deep. And with each discovery, we are reminded of how little we understand. The abyss is not just a place, it is an entire biosphere, vast and varied, stretching across most of our planet and yet almost entirely unexplored. Living without sunlight means living without the rhythms that structure our world, without the energy that drives most ecosystems, without the certainty of plenty. It means adapting to pressure that would crush a tank, to cold that slows metabolism to a crawl, to darkness so complete that light becomes as valuable as gold. And yet, life not only endures here, it thrives. It invents solutions, explores possibilities, and creates forms so strange we sometimes hesitate to call them familiar. The abyss is proof that life's creativity does not dim with the light. If anything, it burns brighter in the dark. As we continue this descent into a realm without sunlight, the strangeness we encounter is not a sign of alienness, but of deep familiarity. It is life doing what it always does, finding a way. It is Earth reminding us that even in the places we think are inhospitable, life has written its story in patient, persistent ink. And as we go deeper, the story will only grow stranger, shaped by forces that few creatures could withstand, and by adaptations that few of us could have imagined. The darkness is not the end of the story. It is where a new one begins, and it is leading us deeper still toward a world where survival is a work of art and the line between the possible and the impossible blurs into shadow. Imagine drifting down through that last sliver of twilight into a darkness so absolute. It feels less like a place and more like a condition. Down here, light is not just scarce, it is an event. A flash of bioluminescence might flare and vanish like a match struck in a cave, a sudden pulse from a fish's lure or a startled shrimp's defence, but otherwise there is only the vast unbroken black, and in that blackness life persists, It doesn't merely exist, it thrives. But thriving here requires more than the usual tricks. In a world without light, with crushing pressure, freezing temperatures and scarce food, survival becomes an art. An intricate, endlessly creative negotiation between biology and environment, written in forms so strange they almost defy belief. To understand how deep-sea creatures survive, it helps to remember that they are not playing by the same rules as surface life. Up there, energy is abundant, delivered daily by the sun. Movement can be swift, growth rapid, reproduction frequent. Down here, everything is rationed. Every calorie is a calculation, every adaptation a compromise between cost and benefit. If a fish can save energy by drifting instead of swimming, it will. If a worm can avoid wasting energy on building hard shells, it will grow soft and flexible instead. If a predator can lure prey rather than chase it, that's exactly what it will evolve to do. The result is an astonishing variety of survival strategies, each shaped by millions of years of trial and error in an environment that punishes waste and rewards ingenuity. Energy efficiency is one of the most important principles of life in the dark. Movement is expensive and meals are unpredictable. Many deep-sea creatures adopt a slow, almost languid lifestyle, conserving energy wherever possible. Fish like the rat-tail and the grenadier drift slowly through the water, using minimal effort to cover large distances. Some jellyfish and siphonophores barely move at all, simply extending their tentacles into the current and waiting for food to drift into their grasp. Even predatory fish, like the fangtooth, which sports teeth so long they can't fully close their mouths, move with a surprising slowness, relying on patience and ambush rather than speed. Every unnecessary motion is avoided. Every joule of energy is accounted for. Feeding strategies reflect the same careful economy. Because food is scarce, many deep-sea creatures are generalists, willing to eat almost anything they encounter. The hagfish, for instance, is both a scavenger and a predator, feeding on carcasses that fall from above as well as burrowing into live prey. Its feeding method is as brutal as it is effective. It uses a rasping tongue to tear into flesh, sometimes crawling inside a carcass to eat it from the inside out. Other species, like the gulper eel, have evolved grotesquely oversized mouths and expandable stomachs, allowing them to swallow prey much larger than themselves. This adaptation means they can take advantage of rare opportunities. If a sizable meal drifts by, they won't have to let it go just because it's too big. Some predators have taken the art of feeding in the dark to theatrical extremes. The anglerfish is a classic example. Rather than expending precious energy chasing prey, it uses a bioluminescent lure that dangles in front of its mouth, mimicking the appearance of a small worm or shrimp. Curious prey, drawn in by the glow, swim directly into the anglerfish's gaping jaws. Other predators use similar strategies. The stoplight loosejaw, a deep-sea dragonfish, emits red bioluminescent light, a rare colour in the deep sea, where most species can't see red wavelengths. This gives the loosejaw a stealthy searchlight, allowing it to illuminate prey without being seen. It's a perfect adaptation to a world where light is both precious and perilous. Camouflage, too, takes on new forms in the dark. On the surface, many animals rely on colours and patterns to blend into their surroundings. In the abyss, where there is no sunlight, camouflage often means being as invisible as possible. Many deep-sea species are transparent, their bodies ghost-like and almost invisible in the water. Others are jet black or red, colours that vanish quickly in the absence of light. Some use counter-illumination, producing a faint bioluminescent glow on their undersides that matches the minimal light filtering down from above. This erases their silhouettes, making them invisible to predators or prey looking up from below. Even predators employ camouflage, mimicking the appearance of harmless drifting debris or small prey to lure in victims. The scarcity of mates is another challenge in the deep, and it has led to some of the most unusual reproductive strategies on Earth. In many species, males are much smaller than females and have evolved ways to ensure they never lose track of a potential mate. The deep-sea anglerfish again offers one of the most dramatic examples. The males are tiny compared to the females and spend their lives searching for a mate in the vast darkness. When they find one, they latch on with their teeth and eventually fuse with her body, sharing her bloodstream and becoming little more than a permanent source of sperm. It's an extreme solution to the problem of isolation, but in a world where encounters are rare, it works. Other species release bioluminescent signals to attract mates, broadcasting their presence across the dark. Some release gametes into the water column, relying on currents and chance to bring them together. Each strategy reflects the same underlying principle. When opportunities are scarce, waste none of them. Even body structure is shaped by the demands of survival in the dark. The crushing pressure of the deep would collapse the lungs and swim bladders of most surface fish. So many deep-sea species have lost these structures entirely. Instead, they rely on oil-filled livers, gelatinous tissues, or cartilaginous skeletons to maintain buoyancy and withstand pressure. The result is often a soft, flabby appearance that seems alien compared to the streamlined shapes of surface fish. These bodies may look fragile, but they are perfectly suited to their environment. Soft tissues compress under pressure without breaking. Flexible bodies bend instead of bursting. In the abyss, strength often comes from softness. Pressure doesn't just shape bodies, it changes chemistry itself. Proteins and enzymes that function perfectly well at the surface can denature, lose their shape and stop working, under the intense pressure of the deep. Deep-sea creatures have evolved molecules called piezolites that stabilize proteins and membranes under pressure, keeping their cells functioning where ours would fail. Even their membranes are different, made of lipids that remain flexible in the cold, high-pressure environment. These adaptations happen at the molecular level, invisible to the eye but essential to survival. Without them, life here would be impossible. Slow growth and long lifespans are another hallmark of deep-sea life. The cold, dark waters slow metabolism to a crawl. Some fish take decades to reach maturity. The Greenland shark, which spends much of its life in deep, frigid waters, grows so slowly that it may live for over 500 years. Coral colonies on deep-sea seamounts can be thousands of years old. This slow pace is not a flaw, it is a strategy. In an environment where food is scarce and reproduction opportunities are rare, a long life increases the chances of success. Growth and reproduction happen on geological timescales, and patience is rewarded. Predator-prey relationships also evolve new dynamics in the dark. Because encounters are rare, many predators must maximize every opportunity. They evolve oversized jaws, expandable stomachs, and teeth designed to hold on to prey once it's caught. Prey species, in turn, develop equally elaborate defenses. Some produce blinding flashes of light to startle predators. Others release glowing fluids or detach luminous body parts to distract attackers while they escape. Some, like the vampire squid, wrap themselves in their arms, turning inside out to present a cloak of spiny projections. In a world where every encounter could mean life or death, evolution has honed both offense and defense into finely tuned tools. Symbiosis, cooperation between species, is another key strategy in the deep. Many bioluminescent animals don't produce light themselves, but rely on symbiotic bacteria housed in special organs. These bacteria convert chemical energy into light, and in return, they receive nutrients and a safe home. Some deep-sea shrimp farm bacteria on their bodies, using them to process chemicals from hydrothermal vents. Tube worms living near vents have no mouths or digestive systems at all. Instead, they host symbiotic bacteria inside their tissues, which convert the vent chemicals into food. These partnerships allow species to exploit resources that would otherwise be inaccessible, turning chemical gradients into energy and survival. The deep ocean also teaches creatures to be opportunists. Carcasses of whales, sharks, and other large animals known as whale falls become islands of abundance in the deep. When one sinks, scavengers arrive quickly: hagfish, sleeper sharks, amphipods, stripping soft tissue within weeks. Later, bone-eating worms and specialized bacteria move in, breaking down the remaining nutrients over years or even decades. These ephemeral ecosystems support entire communities, and many species depend on them. It's a stark reminder of how nothing is wasted in the deep. Even in death, life feeds life. Adaptation in the deep is not just physical or behavioural, it is also ecological. Life here is organised differently than in sunlit waters. Food webs are simpler, often dominated by a few key species. Many organisms are both predator and prey, scavenger and hunter, switching roles as opportunities arise. Competition is less about speed or strength, and more about efficiency and resilience. Cooperation and opportunism are often more valuable than aggression. And because the deep is so vast and uniform, species often have enormous ranges, drifting across entire ocean basins. This connectivity means that the deep ocean functions as a single, vast ecosystem, its parts linked by slow currents and shared resources. Humans have much to learn from these strategies. The deep sea is a masterclass in efficiency, resilience, and adaptation. It shows how life can flourish under conditions that would seem impossible, how scarcity can drive innovation, and how cooperation can unlock new sources of energy. It also reminds us that survival is not always about domination or control. Sometimes it is about patience, restraint, and balance. The creatures of the abyss are not conquerors of their environment. They are in harmony with it, perfectly tuned to its rhythms and constraints. As we look closer at this art of survival, it becomes clear that the deep sea is not merely a hostile environment. It is a crucible of creativity, a place where life's ingenuity is tested and refined in the most extreme conditions. Every strange shape, every eerie glow, every patient ambush is a solution, a biological answer to a challenge that has no parallel on land. And as we descend deeper into this story, the strategies become even more astonishing. The abyss is not done surprising us, and the creatures that call it home are far from finished teaching us what survival can mean. The darkness is not empty, and it is not lifeless. It is alive with invention, alive with persistence, alive with the quiet determination of countless species that have learned to make the impossible ordinary. And as we drift deeper still, into pressure and cold, and the edge of the unknown, we will find that the art of survival is not just about enduring the dark. It is about mastering it, turning it into a canvas on which life can paint some of its most extraordinary creations. Imagine for a moment that you're standing on the deck of a ship in the middle of the open ocean. The waves roll gently beneath your feet, the sky stretches endlessly above, and somewhere far below, deeper than any mountain is tall, lies a world you could never survive in. At the surface, the weight of Earth's atmosphere presses on you with about 1 kilogram per square centimetre, a pressure so ordinary you don't even feel it. But as you descend into the depths, that pressure mounts. Every 10 metres down adds another atmosphere. At 100 metres, it's 10 times what your body is built for. At 1,000 metres, it's 100 times greater. By the time you reach the bottom of the Mariana Trench, nearly 11,000 metres down, the pressure is more than 1,000 times what you feel at sea level. It's the equivalent of having 50 jumbo jets pressing on every square metre of your body. Metal bends, concrete crumbles, and yet somehow life not only endures here, it thrives. This is one of the strangest truths about the deep. Its most extreme condition is also one of its greatest sculptors. Pressure is not just a hazard in the abyss, it is a force that shapes life itself. It molds bodies, rewires biology, slows time, and drives evolution into paths that seem unthinkable from the surface. The creatures that live here are not just adapted to pressure, they are made by it. Their existence is a testament to nature's patience, to millions of years of slow, deliberate experimentation in one of the most hostile environments on Earth. For us, pressure is an enemy. Our bones are rigid, our lungs full of compressible air, our cells balanced to function under the gentle weight of the atmosphere. Even a few hundred meters below the surface, we risk crushed lungs, ruptured blood vessels, and fatal nitrogen narcosis. Submarines and deep-sea vehicles built to resist the abyss must be engineered with walls of thick titanium, their windows made of materials that can withstand the weight of an entire ocean pressing in. But the creatures that call this place home do not resist pressure. They embrace it. Their bodies are not fortresses against the deep. They are shaped to flow with it. One of the most striking features of many deep-sea animals is how soft they are. At first glance, this might seem counterintuitive. Shouldn't a creature living under such crushing force be built like a tank? But rigidity is the enemy here. Hard structures resist compression, and resisting compression means breaking under its weight. Softer bodies, on the other hand, compress with the water around them. Many deep-sea fish, like the cusk eel or the snailfish, lack swim bladders, which would implode under the pressure. Instead, they rely on gelatinous tissues and oil-filled cavities to control buoyancy. Their bones are thin and pliable, their muscles loose and watery. They may look fragile to us, but in the deep they are perfectly designed, not for strength, but for surrender. Even at the molecular level, deep-sea life is shaped by pressure. The proteins in your cells, the tiny machines that drive every chemical reaction in your body, would fold and fail under the crushing force of the abyss. Their shapes would distort, their functions break down. But the proteins of deep-sea creatures are different. They are stabilized by small molecules known as piezolites, which help maintain their shape and function under high pressure. Their cell membranes are rich in unsaturated fatty acids, which remain flexible where ours would become rigid. Their enzymes work efficiently in conditions that would paralyze surface life. Even their DNA replication and repair processes have adapted to the strain. This isn't a superficial adjustment, it's a fundamental rewrite of biology itself. Pressure shapes not just bodies and molecules, but behavior and lifestyle. In the deep, metabolic rates are often astonishingly low. Some deep-sea species grow so slowly that they may take decades to reach maturity. Others reproduce infrequently, investing enormous energy into a small number of offspring. This slow pace isn't laziness, it's necessity. In an environment where energy is scarce and movement costly, patience is a survival strategy. The Greenland shark, for example, grows at a rate of about 1 centimetre per year and can live for over 500 years. Some deep-sea corals grow millimetre by millimetre and have been alive since before the pyramids were built. In the deep ocean, evolution trades speed for endurance. This patience extends to how deep-sea life deals with change. Surface environments can shift dramatically. Seasons come and go, storms rise and fade, temperatures fluctuate by dozens of degrees. The deep, by contrast, is stable. Temperatures remain near freezing, currents move slowly, and light never changes. Because the environment shifts so little, evolutionary changes happen gradually but with profound precision. A mutation that improves pressure resistance might take thousands of generations to spread, but once it does, it is locked in, fine-tuned over millions of years. This is why so many deep-sea species appear ancient. Some lineages, like the coelacanth, have remained largely unchanged for hundreds of millions of years. Others, like certain deep-sea amphipods, are nearly identical to fossils from the age of the dinosaurs. The deep is a place where time stretches and patience pays off. Pressure also shapes size in unexpected ways. One of the most famous deep-sea phenomena is deep-sea gigantism, the tendency for some species to grow much larger than their shallow water relatives. Giant isopods, which resemble oversized pill bugs, can reach lengths of 0.5 metre. Amphipods the size of mice roam the seafloor. The colossal squid, heavier and bulkier than its giant squid cousin, hunts in the cold dark of the Southern Ocean. Scientists are still debating exactly why gigantism occurs, but it may be linked to slow metabolism, longer lifespans, and the need to store energy in a place where meals are rare. A larger body can store more reserves and move more efficiently over long distances, making size a form of survival. Pressure doesn't just sculpt individual creatures, it builds entire ecosystems. On the abyssal plain, vast, featureless expanses of mud and sediment, life spreads thinly but persistently. Sea cucumbers sift through the fine particles, feeding on the rain of organic matter that drifts from above. Tiny worms burrow through the sediment, recycling nutrients. Brittle stars stretch their arms into the current, catching passing food. This world seems still, even barren, but it is alive with slow, patient activity. Every particle that falls is used, every scrap of energy is claimed, and over time, these patient processes shape the chemistry of the ocean itself, locking away carbon, recycling nutrients, and stabilizing Earth's climate. In places where the seafloor cracks and vents, releasing mineral-rich water, pressure shapes life in more dramatic ways. Hydrothermal vent communities are some of the most remarkable ecosystems on Earth, existing entirely without sunlight. Here, pressure keeps water superheated even at temperatures above 300 degrees Celsius, allowing it to dissolve minerals from deep within the Earth. As this water gushes out and meets the cold seawater, minerals precipitate and form towering chimneys. Around these structures, bacteria use the vent chemicals for chemosynthesis, forming the base of a food web that supports giant tube worms, clams, crabs, and fish. These organisms live in a delicate balance between extremes, intense pressure, scalding water, and freezing darkness, and yet they flourish. Without pressure, this entire ecosystem would collapse. Pressure even influences how organisms sense their world. In the absence of light, many deep-sea creatures rely on pressure-sensitive structures to detect movement and vibration. The lateral line systems of deep-sea fish, for example, are often highly developed, allowing them to detect the slightest disturbance in the water. Some species have evolved specialized pressure sensors that help them navigate or locate prey in the darkness. Others use pressure changes to time their vertical migrations, rising toward the surface to feed at night and ascending again by day. Pressure isn't just a physical force here, it's part of the sensory landscape, a constant shaping influence that life has learned not just to endure but to read and use. Patience and pressure together create a kind of evolutionary filter. Only those organisms that can adapt to these twin challenges can survive, and those that do often become specialists in their niche. Some have evolved metabolic pathways that function only at extreme pressures. Others can't survive if brought to the surface. Their proteins unravel, their cells burst, their bodies fail. They are so perfectly tuned to their world that even small changes are lethal. It's a humbling reminder that the deep sea is not an extension of our world, but a different one entirely, governed by rules that would destroy us but sustain them. And yet, these monsters of pressure and patience are not fragile oddities. They are critical players in Earth systems. Deep-sea organisms help regulate global carbon cycles by sequestering carbon in sediments and through their slow, steady metabolic processes. The abyssal plains store vast amounts of carbon, locking it away for centuries. The slow decay of organic matter and the patient work of scavengers and microbes keep nutrients cycling and ecosystems functioning. Even the strange, pressure-built creatures of the deep contribute to the stability of the biosphere. They are not curiosities. They are keystones in the structure of life on Earth. The human relationship with pressure is one of avoidance. We build machines to keep it out, design suits to shield ourselves from it, and treat it as a problem to be solved. But for the creatures of the abyss, pressure is not a problem. It is the foundation of their existence. They are not resisting it. They are written by it. Every soft bone, every pliant membrane, every slow heartbeat is a line in a story authored by the weight of an ocean. And patience is the language in which that story is told, measured not in moments or seasons, but in centuries and millennia. As we continue deeper into this story, it's worth pausing to appreciate just how profound this is. The abyss is not a place where life clings desperately to existence. It is a place where life has mastered the art of turning adversity into opportunity, of shaping itself around the most relentless forces on Earth. The creatures that live here are not survivors in the narrow sense of the word. They are specialists, artisans of adaptation, sculpted by pressure and refined by time. They remind us that evolution is not always about speed or competition or dominance. Sometimes it's about patience, about bending instead of breaking, about thriving not despite the weight of the world but because of it. And as we leave this part of the story behind and drift still deeper, the lessons of pressure and patience stay with us. They will echo in the strange lights that flicker in the darkness, in the silent hunts that unfold without warning, and in the hidden worlds that flourish without sunlight. The abyss is not finished revealing its secrets, and the creatures that dwell here are not done rewriting the rules of what life can be. The next layers of this story will take us even further into that alien night, where glowing signals bloom in the dark and survival becomes a conversation written in light. If there's one thing that defines the deep sea, one thing that transforms its endless darkness from a silent void into a living, breathing realm, it's light, but not the light we know. Down here, sunlight is a distant memory, filtered out and lost long before it can reach the world of the abyss. What remains instead is a scattered constellation of tiny living stars. They flash and fade, drift and pulse, lure and deceive. They are the language and weapon of life in the deep. They are bioluminescence, light born from life itself, and they shape nearly everything about how creatures survive in the gloom. Imagine floating a kilometre below the surface, where the water is black as ink and the pressure could crush steel. There is no horizon, no sunrise or sunset, no hint of the world above. And then, somewhere in that blackness, a light appears. Maybe it's a soft blue glow, pulsing rhythmically as it drifts past. Maybe it's a sharp, sudden flash, like a camera strobe. Maybe it's a tiny point of green, bobbing up and down as if beckoning you closer. This isn't sunlight breaking through, it's life itself lighting the dark. The abyss, for all its emptiness, is alive with these flickers. Some are faint and fleeting, others bright enough to read by. Together they form the most widespread communication system on the planet. Bioluminescence is astonishingly common in the deep ocean. Scientists estimate that up to 90% of deep-sea animals can produce light in some form. It's not a rare talent here, it's the norm. But light is expensive to make. It requires chemical energy, and in a place where energy is precious, nothing is wasted. That means every flash, every glow, every flicker serves a purpose. This isn't random decoration. It's a tool honed by evolution over millions of years, and creatures wield it with extraordinary precision. At its core, bioluminescence is a chemical reaction. A light-producing molecule called luciferin reacts with oxygen, often aided by an enzyme called luciferase. The reaction releases energy in the form of light. It's the same principle behind the glow of a firefly or the sparkle of certain fungi on land. But in the deep sea, nature has taken this reaction and turned it into an art form. Different species use different types of luciferin, producing different colours and intensities of light. Some control the reaction with exquisite precision, producing quick flashes or slow, steady glows. Some house symbiotic bacteria that produce light for them, cultivating these microbes in specialised organs. Others generate light directly within their own tissues. The reasons for producing light are as varied as the creatures that use it. One of the most obvious uses is hunting. The classic example is the anglerfish, whose bioluminescent lure dangles like a glowing worm just in front of its mouth. Prey, drawn by the light in the darkness, swims close and is swallowed whole. Other predators use light to mimic prey more directly. Some deep-sea squid have glowing tips on their tentacles that resemble small fish or plankton. When a curious victim approaches, the squid's tentacles snap shut. Even more devious are the cookie cutter sharks, which use bioluminescent bellies to blend in from below, hiding their silhouettes as they approach larger animals from underneath. Bioluminescence is not just a weapon, it's also a shield. Many prey species use light defensively, and the tactics can be ingenious. Some squid eject glowing clouds instead of ink, creating a luminous distraction while they slip away into the dark. Certain shrimp release bioluminescent mucus when attacked, coating their predators in light and making them targets for larger hunters. Some small fish flash bright lights to startle predators or disorient them long enough to escape. Others use light to disappear altogether. In a phenomenon called counter-illumination, many deep-sea animals match the faint downwelling light from above with bioluminescent organs on their bellies. This erases their shadows and makes them nearly invisible from below, a trick that turns light into camouflage. Communication is another vital function of light in the deep. In a world without sunlight, bioluminescence becomes a language. Some species flash coded signals to attract mates, each species with its own unique pattern, like a biological Morse code. Certain lanternfish use light organs arranged in species-specific patterns that help them recognize one another in the darkness. In the vast emptiness of the deep, where individuals may be separated by hundreds of meters, light is often the only way to find one another. And once they do, light can continue to play a role in courtship, guiding partners together in a darkness so complete they might otherwise swim past each other without ever knowing. For some species, bioluminescence even shapes their social structures. Siphonophores, colonial organisms made up of many specialized units, use light to coordinate their movements, flashing signals along their bodies as they drift through the water. Deep-sea squid communicate with shifting patterns of light across their skin, changing signals on the fly. These displays can coordinate hunting, deter rivals, or confuse predators. In the absence of sound and vision, light becomes a kind of touch, a way for life to connect across distance and darkness. Perhaps the most extraordinary thing about bioluminescence is how widespread and varied it is. It appears in nearly every major group of marine life: fish, squid, shrimp, jellyfish, comb jellies, even bacteria. It has evolved independently dozens of times, each lineage finding its own way to make light. That repeated evolution speaks volumes about its importance. In the deep ocean, where light is rare, the ability to create it is one of the most powerful tools life can possess. It's so valuable that evolution has reinvented it again and again, each time refining it into new forms and functions. The diversity of bioluminescent strategies is staggering. Some creatures like the flashlight fish store symbiotic bacteria in special pockets near their eyes, opening and closing these pockets to blink on and off. Others, like certain jellyfish, produce light in response to touch, creating rippling waves of colour that spread across their bodies. The comb jelly uses rows of cilia to scatter light into shimmering rainbows, a phenomenon called iridescence that isn't true bioluminescence but still adds to the spectacle. The stoplight loosejaw produces two different colours of light: red for stealthy hunting and blue for general illumination, an adaptation that gives it an edge in a world where most animals can't even see red. One of the most haunting displays belongs to the siphonophores. Some of these colonial drifters stretch for tens of meters, longer than a blue whale, and glow with thousands of tiny lights along their length. These lights may lure prey, confuse predators, or help coordinate the colony's movements. Seen from a distance, they look like a living constellation drifting through the dark, a galaxy of biological lanterns floating in a sea of black. Bioluminescence can also reveal the deep in unexpected ways. When submarines or remotely operated vehicles descend into the abyss, their lights sometimes attract swarms of bioluminescent creatures. The disturbance can trigger spectacular displays: clouds of glowing particles, swirling halos of light, sudden explosions of brilliance. Even the passage of a large animal, like a squid or a whale, can set off waves of glowing plankton, tracing the creature's path like a comet's tail. It's a reminder that the deep is not empty. It's alive and reactive, and light is the medium through which it responds. The ecological consequences of bioluminescence are profound. Light shapes predator-prey dynamics, influences mating and migration, and structures entire food webs. It can even shape evolution far beyond the deep sea. Some researchers believe that the development of eyes capable of detecting bioluminescence was a key driver of early vertebrate evolution. Others argue that bioluminescent signaling could have influenced the evolution of social behavior in certain species. In this way, the glow in the gloom is not just a feature of the deep. It is a force that ripples outward, shaping life in ways we're only beginning to understand. Humans have barely begun to explore the potential of bioluminescence. Scientists are studying luciferin and luciferase for use in medical imaging, disease detection, and even sustainable lighting. Bioluminescent markers are already used in genetic research, helping scientists track cellular processes in real time. And beyond the practical, there is the philosophical. Bioluminescence challenges our assumptions about life. It reminds us that light does not belong only to the sun or to fire. Life itself can create it, wield it, and shape it into tools and messages. Even in the deepest darkness, life finds a way to shine. It's worth remembering too that most of the deep's bioluminescent secrets are still hidden. Every expedition seems to uncover something new. A jellyfish with a previously unknown light display, a fish with organs arranged in a pattern no one has seen before, a bacterium with a novel chemical pathway for producing light. Because so much of the deep remains unexplored, our understanding of bioluminescence is still fragmentary. The patterns we know are only part of a much larger story, one that stretches across millions of species and billions of years. What we do know is that the glow in the gloom is more than just a beautiful spectacle. It's a fundamental part of how life works in the abyss. It's how predators hunt and how prey escape, how mates find each other and how species communicate, how ecosystems are built and how they endure. It's the language of a world without sunlight, a conversation written in flashes and glows instead of words or sound. It turns the deep from an empty void into a dynamic, vibrant realm. And perhaps most importantly, it teaches us something about life itself. Even when stripped of the most basic elements we associate with living, light, warmth, abundance, life doesn't fade, it adapts, it invents, it creates light out of darkness, and uses it to build new ways of being. The deep sea's glow is a living metaphor for that resilience. It is proof that even in the most hostile places, life finds not just a way to survive, but a way to flourish, to communicate, to hunt, to love, to build worlds of its own. As we drift deeper into this world, following those scattered constellations of living light, it's clear that the abyss is far from empty or dead. It's alive with signals and stories, written in flashes and pulses that hint at complex behaviours we're only beginning to decipher. And those glimmers lead us onward, deeper into the hidden lives of the creatures that dwell here, toward even stranger strategies and subtler forms of adaptation. The dark is not silent, and it is not still. It speaks in light. And if we listen closely, we might just begin to understand what it's saying. In the deep sea, where sunlight never reaches and the world is defined by darkness, the art of hiding becomes more than a useful trick. It becomes a matter of life and death. Down here, where food is scarce and the stakes are always high, survival often depends on remaining unseen until the perfect moment. It might mean waiting motionless for a prey animal to drift by, completely unaware of the predator lurking just inches away. It might mean vanishing into the blackness before a hungry mouth closes around you. It might mean pretending to be something you're not, a harmless speck of drifting debris, a glow that looks like a meal, a shape so alien that predators don't recognize it as food at all. In this world, deception is not just cleverness. It is evolution's sharpest tool, honed by millions of years of predatory arms races and desperate escapes. If light is the language of life in the deep, invisibility is its dialect. But invisibility here does not work the way it does in the bright world above. Up there, camouflage often means colour, blending with a leafy background, mimicking bark or sand, adopting the hues of flowers or coral. Down here, colour is irrelevant. In the absence of sunlight, most of the visible spectrum disappears. Reds vanish first, then oranges and yellows, until only deep blues remain. Beyond a few hundred metres, even blue fades, and the world is reduced to blackness broken only by the occasional pulse of bioluminescence. In such a place, invisibility is about physics and biology, not pigment. It's about bending light, absorbing it, scattering it, or not producing it at all. One of the simplest strategies is transparency. Many deep-sea creatures, from small crustaceans to gelatinous jellies, are nearly invisible because their bodies are made of tissues that let light pass through. Without pigment to absorb or scatter what little light exists, they become ghost-like, almost impossible to see. The glass squid, for example, is so transparent that its internal organs are visible. Even its eyes, which would normally betray its presence, are reduced to thin, rod-like structures that create minimal shadows. The barrel fish takes this even further, with a completely transparent head that allows its upward-pointing eyes to spot the silhouettes of prey above without exposing its position. Transparency is one of the most effective forms of camouflage in the deep, a solution so simple and elegant that evolution has reinvented it countless times. Other species take the opposite approach. Instead of letting light pass through, they absorb it completely. Many deep-sea animals are covered in skin so black it reflects almost no light at all. Some of these ultra-black fish reflect less than 0.05% of the light that hits them, making them practically invisible even when illuminated by the powerful lights of deep-sea submersibles. This ultra-black camouflage works by trapping light within microscopic structures in the skin, where it bounces around and is absorbed instead of reflected. Predators and prey alike can pass within centimetres of these animals and never know they're there. In a world where light is precious and rare, absorbing it all is as effective as bending it away. Some creatures hide not by disappearing, but by blending perfectly into the faint light that does exist. Counter-illumination is one of the most remarkable strategies in the deep-sea playbook. Many fish, squid and shrimp have photophores, small light-producing organs, arranged along their bellies. These photophores emit a faint glow that matches the downwelling light filtering from above. From below, this erases the animal's silhouette, rendering it invisible against the dim backdrop. Counter-illumination is not static, it's adjustable. These creatures can fine-tune the intensity and wavelength of their glow in real time, responding to changes in light conditions as they move through the water column. It's an active camouflage system, one that requires precision and constant feedback, and it shows just how sophisticated evolution solutions can be. But deception in the deep isn't always about hiding. Sometimes, the best way to catch a meal is to pretend to be one. The anglerfish's lure is perhaps the most famous example, a glowing appendage that mimics the flicker of a small worm or shrimp, irresistibly attractive to curious prey. But the anglerfish is far from alone in this trickery. The black dragonfish has a barbel, a long trailing filament under its chin, tipped with a glowing organ that it can wiggle and pulse to mimic prey. The stoplight loosejaw uses a combination of red and blue light to approach prey unseen and then illuminate it at the last second. Even siphonophores, colonial relatives of jellyfish, can mimic schools of small fish with their glowing bodies, luring predators into a deadly trap. Mimicry is not limited to light. Some species imitate shapes, textures, or even behaviours to deceive predators or prey. Certain deep-sea shrimp adopt the drifting, tumbling motion of marine snow, the constant rain of organic debris that falls from the surface. By moving like inanimate particles, they avoid detection by predators scanning for movement. Some gelatinous creatures mimic the appearance of other, more dangerous species. Others look like pieces of detritus, too unappetizing to bother with. In the deep, where visibility is limited and sensory information is scarce, even crude mimicry can be highly effective. One of the most remarkable examples of deep-sea deception involves a group of squid known as vampire squid, although they're not true predators at all. When threatened, a vampire squid can invert its body, wrapping its arms and webbing around itself to present a spiny, unappetizing surface to would-be predators. It can also eject a cloud of bioluminescent mucus, creating a glowing distraction while it escapes. The combination of bluff and misdirection is extraordinarily effective. To the predator, the vampire squid suddenly seems to transform into something larger, more dangerous, or simply too confusing to pursue. Invisibility and deception aren't just for prey. Predators use them too, often with deadly efficiency. Some deep-sea sharks are covered in light-absorbing skin, allowing them to approach prey undetected. Others use counter-illumination to erase their silhouettes from below, sneaking up on unsuspecting fish from beneath. Some predators remain motionless for hours, blending into the background until a meal drifts close enough to strike. In a place where speed is costly and visibility is limited, patience and disguise often work better than a chase. Camouflage in the deep isn't limited to individual bodies. It extends to behavior and strategy. Many deep-sea creatures engage in vertical migration, rising toward the surface at night to feed and descending again before dawn. By timing their movements with the daily cycle of light, they reduce their chances of being seen by predators. Others coordinate their bioluminescent signals to confuse or overwhelm attackers. Some species swarm in coordinated patterns, creating the illusion of a single, much larger organism. These behaviors are forms of deception too, turning the challenges of the deep into opportunities. The sensory environment of the deep also shapes how disguise and deception evolve. Because light is scarce, many animals rely on other senses, pressure, vibration, chemical signals, to detect prey or avoid predators. Camouflage must account for these senses too. Some species move slowly or not at all to avoid creating detectable vibrations. Others release chemicals that mask their scent or confuse predators' sensory systems. Deception here is multi-layered. It's not just about what you look like. It's about how you move, how you smell, how you feel in the water. Even reproduction in the deep can involve deception. Some species use bioluminescent displays to attract mates, but these signals can also lure predators. As a result, some animals have evolved ways to disguise their courtship signals, making them harder for predators to detect. Others use false signals to confuse rivals or mislead potential mates into revealing their positions. It's a reminder that deception is not just a matter of survival, it's woven into every part of life in the abyss. What makes all of this so remarkable is that it happens in an environment that seems, at first glance, too simple for such complexity. The deep ocean appears uniform, dark, cold, vast and empty, but that simplicity is deceptive in itself. Within those constraints, evolution has produced a staggering diversity of strategies for hiding, mimicking, tricking and deceiving. Each adaptation is a solution to a specific challenge: how to hunt without being seen, how to avoid becoming prey, how to find a mate in the dark, how to exist in a place where even the smallest mistake can mean death. Our attempts to study these strategies are often hampered by how well they work. Many deep-sea creatures are so transparent they are nearly invisible even under bright lights. Others disintegrate when brought to the surface, their delicate bodies unable to withstand the pressure change. Some are so rare or elusive that we know them only from a few fleeting glimpses on camera. What we do know is that we're only scratching the surface. Every dive into the deep reveals new forms of deception, new ways that life has learned to hide and trick and survive. The mastery of disguise and deception in the deep is not just a curiosity. It's a testament to life's creativity. It shows that even in the harshest, most alien environments, evolution doesn't just solve problems, it does so with elegance and subtlety. It turns scarcity into opportunity, darkness into a canvas for invisibility, and stillness into a weapon. It blurs the line between predator and prey, between signal and noise, between life and background. And as we continue deeper into this realm, it becomes clear that the abyss is not a place where life merely survives. It is a place where life innovates endlessly, turning even the simplest elements, darkness, pressure, chemical gradients, into tools of extraordinary sophistication. The disguises and deceptions of the deep are more than survival strategies. They are works of evolutionary art, masterpieces shaped by millions of years of relentless experimentation. And they lead us onward, deeper into a world where even time itself seems to stretch and bend under the weight of the ocean, and where patience becomes as vital a survival skill as invisibility itself. Time is a slippery thing in the deep. On the surface, we measure it in sunrises and sunsets, in tides and seasons, in the steady rhythm of days that shape our lives. Light dictates everything. When plants bloom, when animals migrate, when predators hunt and prey hide. It's so ingrained in how we think about life that it's hard to imagine a world where time has no such anchors. But below the reach of sunlight, time unravels. It stretches and slows until it feels less like a ticking clock and more like a vast patient current. Down here, there is no dawn to signal the start of a day, no shifting seasons to mark the passage of a year. The deep sea exists in a near-eternal twilight, and the creatures that live here have evolved to move to a different rhythm, one dictated not by the sun above but by the slow, unhurried pulse of the abyss itself. It's difficult to appreciate just how profoundly this changes everything. The deep sea is a place where movement is measured in centimetres per second, where meals may be separated by weeks or months, where generations stretch over centuries. Cold water slows chemical reactions and metabolic processes, and scarcity makes every bit of energy precious. Together, these forces create an environment where rushing is not just unnecessary, it's dangerous. Survival here depends on patience, on doing more with less, on stretching every calorie and every moment as far as it can go. Life down here is not a sprint, it's a long, slow dance. One of the clearest signs of this slow pace is growth. Many deep-sea species grow at rates that would be inconceivable at the surface. The Greenland shark, for example, may live for more than 5 centuries, growing just a centimetre or 2 each year. Some species of deep-sea rockfish live for over 200 years. Deep-water corals grow millimetre by millimetre, forming vast reef structures that are thousands of years old. Even the microbial communities that coat hydrothermal vents evolve slowly, changing composition over decades instead of days. This glacial pace isn't a flaw, it's a strategy. In a world where food is scarce and temperatures hover near freezing, slow growth conserves energy and reduces the need for constant feeding. Reproduction follows the same patient rhythm. Many deep-sea animals don't reproduce every year. Some spawn only once in a lifetime, investing enormous energy into a single, carefully timed effort. Others release small numbers of offspring after long gestation periods, ensuring that each one has a better chance of survival. Brooding times can stretch into months or even years. In some deep-sea octopuses, females guard their eggs for more than 4 years without eating, a vigil unmatched in the animal kingdom. That kind of patience would be impossible in a faster, more competitive environment. But here, where time itself seems to move differently, it works. Even death unfolds slowly in the deep. A whale fall, the carcass of a whale that sinks to the seafloor, can support an entire ecosystem for decades. First, scavengers strip away the soft tissue, a process that might take months. Then, worms and microbes move in, breaking down the bones and releasing nutrients that feed generations of organisms. Over time, the whale's remains become part of the sediment, contributing to the slow accumulation of organic material that blankets the abyssal plain. What happens in days or weeks on land takes years here, each stage unfolding with deliberate, unhurried precision. This stretching of time has profound effects on evolution itself. On the surface, where environments change rapidly and competition is fierce, evolution often favours speed, fast growth, early reproduction, rapid adaptation. In the deep, stability rules. Temperatures are constant, light is absent, and the physical environment changes little over millions of years. As a result, evolution here is less about quick responses and more about long-term refinement. Many deep-sea species are ancient lineages, barely changed from their ancestors of tens or even hundreds of millions of years ago. The coelacanth, once thought to be extinct, is a living fossil from the age of dinosaurs. Certain amphipods and sea cucumbers are nearly identical to species preserved in Jurassic sediments. They don't look primitive because they failed to evolve. They look primitive because they haven't needed to. The deep has remained largely the same, and so have they. Time moves differently even for ecosystems. Hydrothermal vents, for instance, are born, flourish, and die over decades or centuries. A new vent might appear after a volcanic eruption, rapidly colonized by bacteria and the animals that depend on them. Over time, the vent cools and its chemical output dwindles, and the community it supports fades away. The entire life cycle of a vent field, from birth to extinction, can span a human lifetime or two, yet within that span, species may evolve unique adaptations found nowhere else. The abyssal plain accumulates organic material at an almost glacial pace, perhaps a centimetre of sediment every 1,000 years. The seamount coral forests that rise from these plains may take tens of thousands of years to grow. In a world defined by such timescales, sudden change is rare and often catastrophic. This slow pace of life extends to the rhythms of behaviour as well. Many deep-sea creatures are ambush predators, content to remain motionless for hours or days until prey wanders close enough to strike. Some scavengers detect chemical traces of food drifting through the water and spend days following them to their source. Even the great migrations of the deep are slow and deliberate. Every night, billions of animals rise from the depths to feed in the surface waters, then descend again before dawn. This vertical migration, the largest daily movement of biomass on Earth, happens at a pace dictated by the slow beats of deep-sea hearts and the sluggish pull of cold water. The deep ocean's patience is not just a consequence of its environment, it's a necessity for survival. When resources are scarce, rushing wastes energy. When conditions are stable, speed offers little advantage. And when pressure and cold conspire to slow life's chemistry, trying to move faster simply isn't an option. Patience becomes not just a virtue but a form of adaptation, as fundamental as gills or fins. Every heartbeat, every breath, every cell division in the deep is measured and deliberate, part of a larger choreography that unfolds over centuries instead of seconds. This has surprising consequences for how deep-sea species interact. Because individuals live so long and reproduce so slowly, populations tend to be small and stable. Competition is often less intense than in surface ecosystems, where rapid growth and reproduction drive constant battles for space and resources. Instead, deep-sea communities tend toward balance. Predators and prey exist in a kind of equilibrium, with population fluctuations unfolding over decades rather than seasons. Symbiotic relationships too can last far longer. Tube worms and their bacterial partners may remain together for decades, each dependent on the other's slow, steady contributions. The slow passage of time in the deep also influences how we, as humans, study it. Our science is built on short timescales, years, decades at most, but the deep operates on scales that dwarf our own. A coral that grows a centimetre in a century will not reveal much in a 3-year study. A fish that reproduces once every few decades may appear stable or rare simply because we haven't observed it long enough. Many of the processes that shape the deep unfold too slowly for us to witness directly. They require patience to study, patience to understand, a kind of scientific humility that matches the patience of the abyss itself. There's a poetic irony in this. The deep sea, which seems so alien and remote, may actually be more representative of life on Earth than the bustling sunlit world we know. The majority of Earth's biosphere exists in this slow-motion realm. Most of the planet's living space is cold, dark, and under immense pressure. The creatures that inhabit it are not anomalies. They are the norm. It is we, living in the thin, bright skin at the surface, who are the exceptions. The slow dance of the deep is not an outlier. It is the default tempo of life on our planet. This slow tempo carries lessons for us. In a world obsessed with speed and growth, the deep sea is a reminder that patience can be powerful. It shows that life does not always need to rush to succeed. It can take its time, refining solutions over millions of years, building resilience instead of speed, balance instead of dominance. It shows that ecosystems can thrive not by constant change, but by long-term stability. It reminds us that time is not a universal constant in the experience of life. It is a flexible, malleable thing, shaped by environment, pressure, temperature, and scarcity. Even the very geology of the deep reflects this slow rhythm. Seafloor spreading at mid-ocean ridges moves crustal plates apart at rates measured in centimetres per year. Sediments settle in delicate layers that record millions of years of history. Currents flow sluggishly through the deep, taking centuries to complete their global circuits. The ocean's great conveyor belt is the system of currents that moves heat, nutrients and carbon around the planet. Takes 1,000 years to make one full loop. Down here, time doesn't march forward. It drifts, spirals and eddies like the water itself. And yet, for all its slowness, the deep is not stagnant. Change does happen here, and when it does, its effects ripple for centuries. A shift in climate at the surface can alter the amount of organic matter that sinks to the depths, reshaping food webs for generations. A volcanic eruption on the seafloor can create a new hydrothermal vent field, seeding a brand new ecosystem. Even human actions, deep-sea mining, pollution, climate change, can leave marks that will persist for millennia. The deep may move slowly, but it remembers. To exist in the deep is to be part of this slow dance, to live in harmony with a rhythm measured not in heartbeats, but in geological time. It means growing at a pace that seems impossible on land, reproducing only when the conditions are right, and building lives that stretch far beyond the span of human experience. It means seeing patience not as passivity but as strength, the strength to endure, to persist, to adapt without haste. As we continue deeper into this world, it becomes clear that the slow dance of time below is not a quirk or a curiosity. It is the defining feature of the abyss. It shapes every adaptation, every behaviour, every ecosystem. It is written into the bones of fish and the branches of corals, into the flows of water and the layers of sediment. It is a reminder that time is not a fixed thing, but a living dimension of the natural world, stretching and bending to fit the needs of life. And as we drift onward, deeper still, we will see that this slow, deliberate rhythm is not confined to individual creatures, or even to life itself. It extends to the very edges of possibility, where ecosystems are built on chemicals instead of sunlight, where life thrives in places once thought barren, and where the limits of what we believed possible dissolve in the darkness. The next part of this journey leads us there, to the edges of existence where life lives not just slowly but daringly, perched on the boundary between possible and impossible. Down here in the endless dark where pressure crushes and sunlight is only a rumour, life is supposed to stop. That was what scientists once believed, that below a certain depth, the ocean was a barren, silent place, too hostile and too remote for anything to survive. For centuries, the abyss was thought of as a dead zone, a cold grave beneath the living sea above. And yet, as our eyes and instruments have pushed deeper, that belief has crumbled again and again. Not only is the deep sea alive, it is thriving. And nowhere is that more clear than in the places where life clings to existence on the very edge of the possible. It's tempting to think of life as something delicate, easily broken by extremes. On land and in shallow seas, it seems to cluster around mild conditions, moderate temperatures, abundant light, breathable air. But the deep ocean reminds us that life is not fragile. It is stubborn. It is inventive. It finds a way to exist in conditions that defy our imagination, in places that seem fundamentally incompatible with biology. It rewrites the rules of what's necessary and what's possible, and in doing so, it expands our understanding of where and how life can exist. Not just on Earth, but anywhere. Consider the hydrothermal vents that dot the mid-ocean ridges, places where Earth's crust is pulling apart and seawater seeps deep into the planet before boiling back out. The water that gushes from these vents is superheated, sometimes over 400 degrees Celsius, yet it doesn't boil because of the immense pressure. It's laced with toxic chemicals like hydrogen sulfide and heavy metals, and it's utterly devoid of sunlight. And yet, around these vents, life flourishes in riotous abundance. Towering chimneys rise from the seafloor, encrusted with bacteria and draped in mats of microbial life. Giant tube worms, some taller than a person, cluster around the vents, their scarlet plumes waving in the mineral-rich flow. Clams the size of dinner plates lie half buried in the sediment. Crabs scuttle across the blackened rock, and fish drift through shimmering currents of superheated water. The key to these ecosystems is a process called chemosynthesis. Instead of using sunlight to power the creation of organic molecules, as plants and algae do on the surface, the microbes here use chemical energy from the vent fluids. They oxidize hydrogen sulfide or methane, harnessing the energy released to build sugars and other molecules that fuel life. These microbes are the foundation of the vent food web, just as photosynthetic organisms are the base of most surface ecosystems. The tube worms, clams, and other animals around the vents rely on them directly or indirectly, feeding on the microbes themselves or on creatures that do. Some, like the tube worms, have gone so far as to form intimate partnerships with these bacteria, housing them inside their bodies in exchange for nutrients. Hydrothermal vent communities are astonishing not just because they exist, but because they exist entirely independently of the sun. They show that sunlight, long thought to be essential for life, is not necessary at all. Life does not need light. It needs energy, and energy can come from many sources. That realization has transformed how scientists think about the universe. If life can thrive in the dark depths of Earth's oceans, feeding on chemicals instead of sunlight, then perhaps it can do the same on other worlds. In the subsurface oceans of Europa or Enceladus, for example, where similar chemical reactions may occur. Vents are not the only place where life thrives on the edge. Cold seeps, places where methane or hydrogen sulfide leaks slowly from the seafloor, host similar communities, though they are less dramatic. Here too, chemosynthetic bacteria form the base of the ecosystem, supporting mussels, tube worms, and other creatures. Some cold seeps are ancient, persisting for thousands of years, while others are transient, shifting as the flow of chemicals changes. Life here is patient and opportunistic, ready to colonize new seeps as they appear and abandon old ones when they fade. Then there are the brine pools, surreal, deadly lakes that sit on the seafloor like puddles within the ocean. These pools are composed of dense, salt-saturated water that doesn't mix with the surrounding seawater. They are often laced with toxic chemicals like methane or hydrogen sulfide, and they are so dense and oxygen-poor that most life cannot enter them and survive. Yet even here, at the edges of these poisonous lakes, life gathers. Mussels and tube worms thrive at the margins, where chemical gradients provide energy for chemosynthetic microbes. Strange fish swim just above the brine, skirting the boundary between life and death. It is a world within a world, deadly just centimetres below, but teeming with life at the edge. Some of the most remarkable examples of life on the edge are not anchored to vents or seeps at all, but instead rely on the sparse rain of organic matter that drifts down from above. This marine snow, tiny particles of dead plankton, fecal pellets, and detritus, is the primary source of energy for much of the deep sea. It falls slowly, taking weeks or months to reach the seafloor, and by the time it arrives, much of its energy has been consumed. Yet life has adapted to survive on this meagre diet. Sea cucumbers crawl across the abyssal plain, vacuuming up the fine sediment in search of organic particles. Tiny worms burrow through the mud, extracting nutrients molecule by molecule. Even bacteria thrive here, breaking down what remains and recycling nutrients back into the ecosystem. It is a sparse, frugal existence, but it is enough. Occasionally, the deep sea receives a windfall, a whalefall, the carcass of a massive whale that sinks to the bottom after death. These events are rare but transformative. A single whalefall can sustain an ecosystem for decades. Scavengers arrive first, stripping the flesh within weeks. Then come specialized worms and microbes that break down the bones, releasing nutrients that feed new waves of life. Entire species are adapted to exploit these ephemeral oases, existing nowhere else. Life seizes these opportunities, expanding and contracting as the resources allow. It is an ecosystem built not on abundance, but on patience and resilience. Even the water itself hosts life on the edge. At depths where pressure would crush most organisms, tiny microbes float in the darkness, metabolizing chemicals at glacial speeds. Some live inside the rocks of the ocean crust, sustained by reactions between water and minerals. Others inhabit the sediments deep beneath the seafloor, where they divide so slowly that their generations span centuries. These are among the most extreme forms of life on Earth, not because they live in obvious extremes of temperature or pressure, but because they persist in conditions so minimal that life seems barely possible at all. They exist at the threshold, clinging to existence where energy is almost non-existent. And yet, they are not dying. They are thriving, slowly, quietly, invisibly. These edge-dwelling communities reveal something profound about life. Its capacity to adapt is far greater than we once believed. Life does not require light, or warmth, or even plentiful energy. It requires only a gradient, a difference it can exploit, and the patience to evolve ways to use it. Where gradients exist, life will follow. It will find ways to capture energy from sunlight, from chemicals, from the decay of radioactive elements, from the slow rusting of iron in seawater. It will adapt to pressures that would crush steel, to temperatures that would boil or freeze most cells, to toxins that would kill almost anything else. Life is not fragile. It is relentless. This resilience has far-reaching implications. If life can exist in boiling vent fluids, or at the edge of toxic brine pools, then it may exist in the icy oceans beneath the crust of Europa, or in the methane lakes of Titan. If it can survive on the sparse energy of marine snow, then it might persist beneath the surface of Mars, living off chemical reactions in the rocks. The deep sea teaches us that life's boundaries are not where we once thought they were. They are far broader, far more flexible, and far more surprising. It also changes how we think about Earth itself. The deep sea is not an isolated alien realm. It is the foundation of the planet's biosphere, covering more than half of Earth's surface and hosting an enormous portion of its biodiversity. The processes that sustain life here, chemosynthesis, nutrient recycling, sedimentation, shape the entire planet. They influence the carbon cycle, regulate the climate, and store vast amounts of organic matter. The life that clings to the edges of the possible is not peripheral. It is central to Earth's story. Yet, despite its importance, much of this realm remains unexplored. We have mapped the surfaces of Mars and the Moon in more detail than the deep ocean. Vast regions of the abyss have never been visited, and countless species remain undiscovered. Each new expedition reveals life in places where none was expected. Fish living in the Hadal trenches, microbes thriving deep within the crust, entire communities clustered around seeps that were unknown just years ago. The more we look, the more we realise how much we have yet to learn. And perhaps that is the most humbling lesson of all, that life does not conform to our expectations. It does not stop where we think it should. It pushes past every boundary we draw, expanding the map of the possible until the impossible becomes commonplace. The deep sea is not a world of limits. It is a world of possibilities, a living demonstration of evolution's creativity and persistence. It shows us that life is not defined by its environment. It defines the environment, shaping and reshaping it in a continuous dance of adaptation. As we continue our descent into this alien realm, the edges of the possible keep moving outward. What once seemed unimaginable, life without sunlight, life without oxygen, life under crushing pressure, is now known to be common. And as we follow that thread deeper, we begin to see that the abyss is not just a place where life survives. It is a place where life thrives in ways we never anticipated, where the improbable becomes inevitable, and where the boundary between Earth and the cosmos begins to blur. That boundary is where we go next, into a realm where time itself folds back on itself, and where the past and present coexist in living form. A place where ancient lineages still swim, unchanged and unhurried, like ghosts from Earth's earliest days. If you were to drift far enough into the deep, past the glowing flashes and silent hunters, beyond the forests of tube worms and the great plains of soft sediment, you would find yourself in a realm where time itself feels different. It is not just the slow pace of life here, though that too contributes to the sensation. It is something deeper, something stranger. It is the feeling of being surrounded not just by living things, but by history itself. Down here, evolution has left behind relics of Earth's distant past, survivors of worlds long gone. They swim and crawl and drift beside creatures born of modern seas, yet they carry in their bodies the memory of eras we know only from fossils. In the deep ocean, the past is not gone, it is alive. The reason for this lies in the nature of the abyss itself. On land, environments change rapidly. Mountains rise and erode, rivers carve new paths, climates shift from ice age to greenhouse and back again. Life must adapt quickly or vanish. But the deep sea is different. It is remarkably stable. Temperatures remain near freezing, pressures unchanging, darkness eternal. Even over millions of years, the physical conditions here vary little. There are no seasons, no droughts, no wildfires, no sudden frosts. It is a world where stability is the rule, not the exception. And in a stable world, evolution moves differently. There is less pressure to change, fewer incentives to reinvent what already works. As a result, species can persist here almost unchanged for tens or even hundreds of millions of years. Some of the most striking examples of this evolutionary conservatism are the so-called living fossils of the deep. These are species whose bodies have changed little from those of their ancient ancestors, often resembling creatures we know only from the fossil record. One of the most famous is the coelacanth, thought to have gone extinct 66 million years ago. This lobe-finned fish was known only from fossils until a live specimen was discovered off the coast of South Africa in 1938. Coelacanths inhabit deep volcanic slopes hundreds of metres below the surface, where they move with slow, deliberate motions of their paired fins. Fins that are structurally similar to the limbs of early terrestrial vertebrates. Watching a coelacanth swim is like watching a page of evolutionary history come to life, a glimpse into the transition from water to land that shaped all vertebrates, including us. The frilled shark is another ghost from the past. With its eel-like body, 6 pairs of gill slits, and rows of backward-facing teeth, it looks more like a fossil from the Cretaceous than a modern shark. It is in fact part of one of the oldest lineages of sharks, dating back over 80 million years. The frilled shark hunts in slow motion, lunging suddenly at prey with a snake-like strike. Its reproductive cycle is equally ancient and unusual. Gestation may last up to 3.5 years, one of the longest of any vertebrate. It is an animal that seems to belong to a different era, yet it swims quietly through the deep today. Then there are the giant isopods, distant relatives of the pillbugs that roll under rocks in your garden. These deep-sea scavengers patrol the ocean floor at depths of up to 2,000 meters, feeding on carcasses that fall from above. Their lineage stretches back hundreds of millions of years to a time when trilobites still scuttled across the sea floor. Their oversized bodies, some more than 1/2 meter long, and their methodical, almost clumsy movements speak to an ancient way of life, one that has endured because it works. Some deep-sea creatures are not just survivors of ancient lineages, they are virtually unchanged from their fossil ancestors. Horseshoe crabs, though not truly deep-sea dwellers, have close relatives that inhabit deep waters and are nearly identical to species that lived 450 million years ago. Certain deep-sea amphipods and sea lilies look almost exactly like their Jurassic counterparts. Even the enigmatic stalked crinoids, once abundant in Paleozoic seas and thought to have vanished with the age of trilobites, still wave their feathery arms in the deep, anchored to the seafloor by long stalks just as they did hundreds of millions of years ago. What allows these creatures to persist while so many others have vanished is the deep sea's remarkable constancy. Evolution is driven by change, by shifting climates, new predators, emerging competitors. When change slows, so does evolution. It does not stop entirely. Genetic drift and mutation continue, and subtle adaptations accumulate. But the sweeping transformations seen in surface ecosystems, the rise and fall of entire groups of organisms, happen far more slowly here. The deep acts as a kind of refuge, a museum where ancient forms can persist in niches that have existed for eons. This evolutionary stability doesn't mean the deep is static. New species arise here too, and old ones disappear. But the pace is slower, and the transitions are subtler. Instead of dramatic bursts of diversification, evolution in the abyss often refines what already works, polishing existing designs rather than replacing them. That's why coelacanths, frilled sharks and crinoids look much as they did when dinosaurs walked the earth. They are not relics of a stagnant world. They are the products of an environment that rewards endurance and conservatism over rapid innovation. These ancient survivors also remind us of how incomplete our understanding of life on Earth remains. For decades, the coelacanth was known only from fossilized bones, its apparent extinction taken as fact. Then suddenly it was alive again, revealing how little we truly know about the deep. The same may be true of other lineages we think are gone. The ocean is vast and much of it remains unexplored. Entire ecosystems could exist beyond our reach, harbouring species that vanished from the fossil record millions of years ago. In that sense, every expedition into the abyss is also an expedition into Earth's evolutionary history. We are not just exploring space, we are exploring time. The persistence of these ancient species also tells us something about the nature of life itself. It suggests that evolution is not a march toward complexity or intelligence or even novelty. It is a process of adaptation to environment, and if the environment remains the same, then the adaptations that work can persist indefinitely. The coelacanth does not need to change because its world has not. The frilled shark's slow, ambush-based hunting style is as effective now as it was millions of years ago. The giant isopod scavenging lifestyle remains viable because carcasses still fall from the surface, just as they always have. Even the very structure of the deep ocean reinforces this timelessness. The abyssal plains stretch across the planet like vast, unchanging deserts. The water above them circulates slowly, taking centuries to complete a single loop. Sediments accumulate grain by grain, a few centimetres per millennium, preserving the remains of life in delicate layers that record millions of years of history. Down here, change is measured not in seasons but in epochs. The creatures that live here are shaped by that pace. They are slow, deliberate, enduring, built for a world where patience is more useful than speed. And yet, these ghosts are not mere relics. They are active participants in the deep-sea ecosystem. Coelacanths hunt small fish and cephalopods. Frilled sharks help regulate populations of deep-dwelling squid, and giant isopods recycle nutrients from carcasses. They are woven into the fabric of the deep just as tightly as their more modern neighbours. Their survival is not a quirk of history, it is proof of their ecological importance. They have found roles that remain relevant, and those roles keep them anchored in the present even as they carry the past within them. The existence of such ancient lineages in the deep also offers tantalising clues about life's potential beyond Earth. If stability allows ancient species to persist here, then stable environments elsewhere, subsurface oceans beneath ice-covered moons for example, might also harbour life forms that have changed little over immense timescales. They might not resemble the life we know, but they could be just as old, just as patient, just as enduring. The deep sea in this sense is not just a window into Earth's past, it is a window into the possibilities of life everywhere. It's humbling to think that as we peer into the dark waters beneath us, we are not just seeing strange animals, we are seeing echoes of entire worlds that have come and gone. The coelacanth remembers the first vertebrates to walk on land. The frilled shark remembers seas ruled by plesiosaurs and mosasaurs. The crinoids remember a time before trees, when vast shallow seas covered the continents. These creatures are living witnesses to Earth's deep history, survivors of mass extinctions, shifting continents, and changing climates. They are not ghosts because they are gone. They are ghosts because they remind us of what once was, and of what still lingers quietly in the dark. And as we drift further into this realm of living history, the line between past and present begins to blur. Evolution's story is not a straight line but a tangled web, and in the deep, threads from ancient chapters still weave through the present day. They lead us outward too, beyond Earth itself, because the lessons written in the abyss do not stop at the edge of our planet. They reach into the cosmos, where the same principles of patience, persistence, and adaptation might shape life on worlds we have yet to discover. And it is toward that vast cosmic question that our journey now turns, as we follow the clues written in the deep toward the stars beyond. Imagine for a moment standing on the deck of a ship and staring out across the open ocean. To your eyes, it is all one vast, continuous body, the same salt water stretching from shore to horizon, connected and familiar. But beneath that blue skin is another world entirely, a world that, in its darkness, its pressure, its alien chemistry, bears less resemblance to the beaches and coral reefs we know than it does to the icy moons of distant planets. It is Earth, but it is not our Earth, not the one shaped by sunlight and seasons, forests and fields. It is a planet within a planet, ancient and immense, and most of it has never felt the touch of human hands or eyes. This hidden realm is so different, so fundamentally other, that it often feels as though we are visitors not just to another part of our world, but to another world entirely. And the creatures that live here, the glowing hunters, the patient scavengers, the soft-bodied giants, the ghosts from the past, are not just unusual animals. They are reminders that Earth is far stranger and more diverse than the thin layer of sunlight and air where we spend our lives. They are strangers in our own world, yet they belong here as much as we do, perhaps more. Part of what makes the deep ocean feel so alien is how little of it we have seen. More than 80% of the world's oceans remain unexplored. We have mapped the surfaces of Mars and the Moon in far greater detail than the seafloor beneath our own feet. Most of what we know comes from brief expeditions, from the small cone of light cast by a submersible, or the grainy footage of a remotely operated vehicle, every time we descend into the abyss, we find something new. A fish with transparent flesh, a squid with arms like ribbons, a jellyfish that pulses with living light. Many of these creatures are so unlike anything we know that they defy easy classification. They stretch the boundaries of what we think life can be. Even their basic biology often challenges our expectations. Some deep-sea fish have muscles so watery they cannot support their own weight at the surface. Some have bones so delicate they would shatter under the far gentler pressure of shallow water. Others have lost entire organs we consider essential: swim bladders, eyes, even digestive tracts, replacing them with solutions that work only in the deep. Tube worms, for instance, have no mouths or stomachs. Instead, they host symbiotic bacteria inside their bodies that convert chemicals from hydrothermal vents into nutrients. Without their microbial partners, they would starve. Without the worms, the bacteria would have no safe home. Together, they form a single living system, one that could not exist in our sunlit world. Even familiar animals become strange when they descend into the deep. Squid, which in shallow waters are swift and agile hunters, slow to a ghostly drift in the abyss, their muscles adapted for efficiency over speed. Sharks, apex predators at the surface, become sluggish ambush hunters in the cold and dark. Crabs grow long, spindly legs to walk across soft sediment. Eels develop ribbon-like bodies to weave through the narrow crevices of the seafloor. Evolution rewrites the rules, reshaping familiar forms into new alien configurations that look less like Earth's animals and more like creatures from science fiction. And then there are the ones that defy even those comparisons. Some deep-sea creatures seem to ignore the rules of biology altogether. There are fish with mouths too large for their heads, stomachs that can stretch to hold prey twice their size, and teeth that interlock like the gears of a machine. There are jellyfish with bodies so delicate they dissolve when touched, siphonophores that stretch for tens of meters and function as a single organism despite being made up of thousands of specialized individuals. There are creatures that live without oxygen, that generate their own light, that thrive in water so hot it would kill anything from the surface. Each discovery seems to whisper the same truth. Life is far more flexible, far more inventive than we imagine. This alienness extends beyond individual species to entire ecosystems. Hydrothermal vent communities, built on chemical energy rather than sunlight, seem almost extraterrestrial in their logic. Cold seeps, with their methane-fueled food webs, operate according to rules entirely different from those of coral reefs or kelp forests. Even the vast abyssal plains, which at first glance seem barren, host complex networks of scavengers, filter feeders, and microbial communities that live on the thin trickle of organic material from above. These systems have their own rhythms, their own hierarchies, their own relationships. Worlds within worlds, thriving far beyond the reach of sunlight. And yet, for all their strangeness, these deep-sea ecosystems are not separate from the rest of Earth. They are deeply interconnected with the planet's broader systems. The slow rain of organic matter that sustains the abyss begins with photosynthesis at the surface. The carbon sequestered in deep-sea sediments helps regulate Earth's climate. The circulation of deep ocean currents redistributes heat and nutrients across the globe, influencing weather, fisheries, and even the health of coastal ecosystems. The abyss is not just a distant alien place. It is a fundamental part of the living Earth, one that shapes the world above in ways we're only beginning to understand. In this sense, the creatures of the deep are not just curiosities. They are ambassadors from a part of our planet we barely know. They show us that Earth is not simply the world of trees and mountains, rivers and skies that we experience every day. It is also a world of darkness and pressure, of chemical energy and slow, patient time. It is a planet that contains multitudes, and many of those multitudes lie far beneath our feet. Their alien qualities also challenge our ideas about what life must look like elsewhere. When we imagine extraterrestrial life, we often think of forms vastly different from anything on Earth. And yet, in many ways, we don't need to look to the stars to see them. They're already here, drifting in the dark currents and clinging to vent chimneys. If we found tube worms or siphonophores on another planet, we would call them alien without hesitation. If we discovered a fish that glows in the dark and lives without sunlight, or microbes that feed on chemicals in rock and water, we would celebrate them as proof that life exists beyond Earth. But they are already among us, hidden in the deep. The deep sea's alien nature has even shaped human technology and exploration. Engineers designing submersibles and life support systems for space missions often study deep-sea organisms for inspiration. The way these creatures conserve energy, tolerate pressure, and thrive without sunlight offers clues for how we might build systems that sustain life on other worlds. The exploration of the deep and the exploration of space are not separate endeavours. They are reflections of the same question. How does life adapt to the most extreme environments the universe can offer? And as alien as these creatures may seem, they are also deeply earthly. They are products of the same planet that gave rise to oak trees and hummingbirds, wolves and whales. They share the same basic chemistry of life, the same DNA language, the same cellular machinery. Their strangeness is not foreignness, but a different expression of what Earth can do. They remind us that our planet is not limited to the forms we find familiar. It is capable of producing life that feels utterly alien without ever leaving home. Perhaps that is why encounters with deep-sea life are so powerful. They shake our sense of what is normal and possible. They remind us that our understanding of Earth is partial, that our everyday experience is just one thin slice of a far richer whole. They force us to confront the reality that our world is far larger and stranger than we allow ourselves to believe, and in doing so they prepare us for the possibility that life elsewhere in the universe, if and when we find it, may not be as alien as we expect. It may feel familiar, not because it resembles us, but because it resembles the deep. This perspective shifts how we see ourselves as well. It is easy to think of humanity as the pinnacle of evolution, the centre of Earth's story. But the deep sea tells a different tale. It is older than we are, older than the forests and the continents in their current form. It has persisted through mass extinctions, shifting climates, and the slow drift of continents. Its inhabitants have been here since long before we appeared, and they will likely remain long after we're gone. They are not strangers in our world. We are strangers in theirs. As we drift deeper into this realization, the abyss begins to feel less like an alien place and more like a mirror. It reflects back to us the possibilities of life, its resilience, its inventiveness, its capacity to flourish in the unlikeliest of places. It shows us that the boundaries we draw between Earth and space, familiar and alien, past and present, are far more porous than we imagine. And it leads us onward into questions that stretch beyond our planet entirely. Because if the deep sea can host such strange and wondrous forms of life, then what might lie beyond Earth in the hidden oceans of distant worlds? That question is where our journey takes us next, as we follow the clues from the abyss into the cosmic depths where Earth's lessons might help us recognize life among the stars. If you spend enough time drifting in the dark of the deep ocean, watching the slow pulse of bioluminescent signals and the patient choreography of creatures built to withstand impossible pressure, you start to feel as though you are no longer on Earth at all. The familiar landmarks of our world, sunlight, weather, soil and sky, are gone. In their place is a realm where life exists without the things we once believed it needed most. There is no sun, and yet food webs flourish. There is no breathable air, and yet complex animals thrive. There are crushing pressures that would destroy human bodies and delicate machinery alike, and yet here they are, soft and alive and ancient. The longer you look, the more this place begins to resemble another kind of frontier. Not a part of Earth at all, but a glimpse of what life might look like beyond it. This is the quiet revelation at the heart of the abyss. It is not just a strange part of our planet, it is a window into the cosmos. It shows us not only how life adapts to extremes here, but how it might adapt anywhere. It reminds us that our definitions of habitability, sunlight, warmth, a narrow range of pressures and temperatures, are shaped by our experience, not by the limits of biology. And it suggests that the conditions we once considered hostile to life might, in fact, be perfect for it. For most of human history, the search for life beyond Earth was shaped by our own narrow understanding. We looked for Earth-like planets, worlds bathed in sunlight with liquid water on their surfaces and atmospheres that resembled our own. And while those are good places to look, the deep sea teaches us that they are not the only ones. It shows us that life can thrive in places where sunlight never penetrates, where energy comes not from a star but from the slow chemical reactions between rock and water. It shows us that ecosystems can flourish in total darkness, built not on photosynthesis, but on chemosynthesis, the same process that sustains the microbial mats around hydrothermal vents and cold seeps. These lessons have profound implications for the search for extraterrestrial life. Consider Europa, one of Jupiter's moons. Beneath its icy crust lies a global ocean, kept liquid by the tidal flexing caused by Jupiter's immense gravity. That ocean is cut off from sunlight, but it is in contact with a rocky seafloor where chemical reactions could provide the energy for life. Or Enceladus, a small moon of Saturn, where plumes of water erupt from the surface, evidence of a hidden ocean below. The Cassini spacecraft detected organic molecules, salts, and even hints of hydrothermal activity in those plumes, the same ingredients and processes that sustain life around Earth's deep-sea vents. Titan, Saturn's largest moon, has lakes and rivers of liquid methane and ethane on its surface, and possibly a water ocean deep beneath. Even Mars, dry and barren on the surface, may harbour subsurface aquifers where microbes could persist, feeding on chemical gradients. The deep sea gives us a language for thinking about these places. Before we discovered hydrothermal vent ecosystems in 1977, scientists would have laughed at the idea of life existing in complete darkness, at temperatures near boiling without sunlight. Before we found microbes living kilometres beneath the seafloor, they would have doubted that life could persist with so little energy, dividing only once every 1,000 years. Before we mapped the microbial communities around cold seeps and brine pools, they might have insisted that toxins like methane and hydrogen sulfide were universally lethal. But now we know better. We know that life is not defined by the conditions we find comfortable. It is defined by its ability to adapt, and adaptation, as the deep proves, is far more powerful and far more flexible than we imagined. This perspective reshapes how we think about habitability itself. If life can thrive around Earth's hydrothermal vents, then the vents on Europa's seafloor might also host ecosystems. If microbes can persist in the nutrient-poor sediments of the abyssal plain, then similar organisms might exist beneath Mars's surface. If creatures here can survive pressures thousands of times greater than those at sea level, then the crushing depths of an alien ocean might not be a barrier to life at all. The abyss tells us that the range of conditions compatible with life is not narrow. It is vast, and that means the number of worlds where life might exist is far greater than we once believed. The parallels between the deep and the cosmos run deeper still. Both are vast and largely unexplored. Both are environments we cannot survive in without technology. Both challenge our senses and our intuitions, forcing us to rethink what is possible. The same tools we build to explore the deep, pressure-resistant submersibles, autonomous vehicles, remote sensors, are cousins to those we send into space. The same questions we ask about the abyss. How does life survive here? What are its limits? How does it evolve in isolation? Are the ones we ask about the universe. In a sense, every deep-sea expedition is a rehearsal for exploring other worlds. It is practice for thinking beyond the familiar, for recognizing life even when it looks nothing like what we know. The deep also gives us hints about how life might begin. Many scientists believe that hydrothermal vents on the early Earth were the cradle of life itself. In these mineral-rich environments, chemical gradients provided energy, while porous rock structures created natural compartments where simple molecules could concentrate and react. Over time, those reactions may have given rise to the first self-replicating systems, the ancestors of all living things. If life began in the deep here, it might have done the same elsewhere. Europa's seafloor, Enceladus's ocean, or even the hydrothermal systems of ancient Mars could have been nurseries for life, using the same chemistry that sparked biology on Earth. In this way, the Abyss is not just a model for alien ecosystems, it is a model for life's origin itself. It shows us that life does not need a blue sky or a warm surface. It needs water, chemistry, and time, ingredients that are abundant throughout the cosmos. And it shows us that once life begins, it can persist and evolve even in the most hostile environments, adapting over billions of years to conditions we would once have thought uninhabitable. There's another lesson the deep offers us: humility. For most of our history, we believed that Earth was the centre of the universe. Then we learned that it is just one planet orbiting one star among billions. We believed that life was rare, perhaps unique. Then we discovered that life thrives in places we never imagined, in boiling acid springs, in Antarctic ice, in nuclear reactors, and of course in the crushing darkness of the deep sea. Each discovery pushes the boundaries of what we consider possible, and each one makes the universe feel a little more alive. Even the deep itself is not isolated from cosmic forces. The tides that shape its currents are driven by the gravity of the moon and the sun. The chemical elements that compose its water, its rocks, and its life were forged in ancient stars and scattered across the galaxy by supernovae. The heat that powers its hydrothermal vents comes from the slow decay of radioactive elements formed in those same stellar explosions. The Abyss is not a separate world. It is a chapter in a cosmic story that began long before Earth existed and will continue long after it is gone. And just as the cosmos has shaped the deep has shaped the cosmos, or at least our understanding of it. The creatures and ecosystems we study here inform the instruments we build for planetary missions, the experiments we design to test the chemistry of life, and the questions we ask about distant worlds. When we imagine the hidden oceans beneath the icy crust of Europa or Enceladus, we are really imagining Earth's deep sea transposed onto another planet. When we speculate about alien microbes clinging to mineral-rich vents, we are thinking of the bacteria that thrive around vents in the Pacific and Atlantic. When we dream of discovering life elsewhere, we are dreaming of the Abyss, because it has already shown us what is possible. This connection between the deep and the cosmos is more than scientific. It is philosophical. It reminds us that the boundaries we draw between Earth and space, between the familiar and the alien, are illusions. The same physical laws govern the Abyss and the stars. The same chemical reactions that power microbes around hydrothermal vents could power life on another world. The same evolutionary pressures that shape tube worms and anglerfish could shape creatures beneath the ice of a distant moon. The universe is not divided into separate realms of possibility. It is a continuum, and the deep sea is one point along that continuum, one that happens to lie beneath our feet. And perhaps this is the greatest gift the Abyss offers us: perspective. It shows us that our planet is not a closed system, sealed off from the universe. It is part of a vast interconnected cosmos, shaped by forces that reach across billions of years and trillions of kilometers. It shows us that life is not a fragile miracle, confined to a single set of conditions. It is a tenacious, adaptable force that finds ways to exist wherever it can, and it shows us that exploring the unknown, whether it's the dark ocean beneath us, or the dark ocean beneath Europa's ice, is not just about discovery. It is about understanding our place in the universe. As we drift toward the end of our journey through the abyss, this cosmic perspective lingers. The deep sea is not just an earthly frontier, it is a bridge, a link between our planet and the wider universe, between what we know and what we have yet to discover. And as we follow that bridge upward from the crushing depths toward the faint light above, we carry with us a new understanding of what life is and where it might be found. Because the story of the abyss does not end here. It continues in the stars, in the icy moons and distant oceans that await our exploration, and it continues in us, in our endless curiosity and our desire to seek out the unknown, to look into the darkness, whether beneath the sea or beyond the sky, and ask what else might be out there. And with that question echoing quietly in the water, we rise toward the last part of our journey, a return not to the surface itself but to reflection. To what all of this, from the soft glow of bioluminescence to the patient pulse of hydrothermal vents, tells us about ourselves and our place in a universe that is stranger, richer, and more alive than we ever imagined. If you listen closely, the deep sea speaks, not in words or sounds that our ears are trained to hear, but in the quiet language of life itself. It speaks in the slow rhythm of water moving through the black, in the faint pulses of bioluminescent light that flicker like distant stars, in the patient drift of creatures that have no reason to hurry. It speaks in the shapes of bodies honed by pressure and darkness, in the chemistry that fuels ecosystems without sunlight, in the persistence of lineages that remember a world millions of years gone. It speaks too in what it withholds, in the vast stretches of emptiness between living things, in the silence that is not absence but balance. If you stay long enough, if you quiet the noise of your expectations, you begin to understand that the deep is not empty at all. It is alive, ancient, and profoundly aware. Not in the way a human is aware, but in the way an ecosystem is. A living system that has been thinking and adjusting and evolving for longer than we have existed. We often think of exploration as conquest, as a matter of going somewhere, planting a flag, collecting data, and returning with answers. But the deep resists that approach. It is not a place that reveals itself easily or quickly. It rewards patience and humility, the willingness to observe without fully understanding, to accept that some mysteries will remain beyond us. Even the most advanced submersibles and remote vehicles can only glimpse tiny portions of it. Even our most careful studies capture moments, not centuries. The deep is older, slower, and more complex than our tools or our timescales can easily grasp. To learn from it, we must do more than explore. We must listen. Listening, in this sense, means recognizing what the deep is telling us about life itself. It tells us that life is resilient. It thrives where it should not, in the cold and the dark, under pressures that would crush us, feeding on energy sources that seem meager or toxic. It tells us that life is inventive, finding ways to solve problems we didn't even know existed, turning poison into food, turning darkness into communication, turning scarcity into abundance. It tells us that life is patient, evolving slowly when the environment allows, enduring for hundreds of millions of years without needing to change. And it tells us that life is interconnected, woven into systems that stretch from the seafloor to the atmosphere, from ancient microbes in rock pores to the carbon cycle that shapes our climate. It also tells us that our view of the world is incomplete. We build our understanding around the thin skin of the biosphere we inhabit, the world of sunlight and air, of seasons and weather. But that world is only a fraction of Earth. The deep ocean alone accounts for more than half of the planet's habitable space. Most of Earth's living space is not bright or warm or familiar. It is dark, cold and remote, and yet it is teeming with life. If we build our definitions of what is normal based on the surface, we miss the true nature of our planet. The deep shows us that Earth is not just the world we walk on. It is also the world that lies far beneath us, hidden from view, shaping the rest of the biosphere in ways we're only beginning to understand. Listening also means hearing what the deep has to say about time. On the surface, we measure time in days and seasons, in growth and decay, in the rapid churn of ecosystems that change from year to year. In the deep, time stretches. It moves with the slow drift of currents and the even slower accumulation of sediments. It pulses in centuries-long lifespans and millennia-old coral forests. It unfolds over millions of years in the persistence of species that have barely changed since the age of dinosaurs. This slow rhythm is not a delay or a deficiency. It is the natural pace of life in a stable world. It reminds us that change does not always have to be fast to be profound, that evolution is not always dramatic to be powerful. It reminds us that patience is not the opposite of progress. Sometimes it is progress. And there are lessons too in how the deep connects us to the rest of the universe. The ecosystems that thrive around hydrothermal vents show us that sunlight is not the only path to life. The microbes that persist deep beneath the seafloor show us that life can endure with almost no energy. The strange adaptations of deep-sea creatures show us that biology is capable of far more than we imagined. These lessons reach far beyond Earth. They shape how we search for life on other worlds, and how we think about where life might arise. They remind us that the conditions for life are not rare or precious. They are scattered throughout the cosmos, and wherever they exist, life may follow, not because it is easy, but because life is persistent. But perhaps the most important thing the deep tells us is about ourselves. In the face of its immensity and its age, our species is small and young. Our knowledge is partial. Our reach is limited. We have explored more of the surface of Mars than of our own sea floor. We have mapped the cosmic microwave background in greater detail than the abyssal plains beneath the Pacific. We are a species still taking its first tentative steps into the unknown. And yet, our curiosity drives us forward. It pushes us into the dark with fragile machines and limited knowledge, not because we are certain of what we will find, but because we want to know. That desire to explore, to question, to listen, is as much a part of us as the abyss is a part of Earth. The deep invites us to approach the unknown not as conquerors, but as students. It reminds us that discovery is not about imposing our expectations on the world, but about letting the world expand those expectations. It reminds us that the universe is richer, stranger, and more surprising than we imagine, and that our task is not to tame it, but to learn from it. It invites us to replace certainty with curiosity, control with wonder, and in the quiet of that invitation, something shifts. The abyss stops feeling like a distant, alien place and starts to feel like part of a larger story. The story of life's persistence, of Earth's hidden depths, of the universe's vast possibilities. It becomes not just a place we visit, but a teacher we return to again and again, listening for the next lesson it has to offer. If you listen long enough, the deep also reveals something more intimate, a reflection of ourselves. The creatures that glow in the darkness, that build lives from scarcity, that endure against all odds, are not just curiosities. They are reminders of the same resilience and creativity that define life everywhere, including us. We too are part of this story. We too are shaped by the same forces, built from the same elements, driven by the same impulse to adapt and survive. The abyss is not separate from us. It is part of us, just as we are part of it. And that may be the deepest lesson of all. The abyss shows us that life's story is not confined to the familiar or the visible. It is not a tale told only in sunlight and air. It is a story that reaches into darkness, that thrives in silence, that persists under pressure. It is a story written in every glowing pulse of light, every slow drift of a jellyfish, every ancient lineage that still swims in the cold. It is a story that began long before we arrived, and will continue long after we're gone. Listening to the deep means understanding that story and recognizing that it is still unfolding. It means accepting that our planet, and perhaps the universe itself, is not finished. It is still changing, still surprising, still full of mysteries waiting to be revealed. It means embracing the unknown not as something to fear, but as something to explore. And so, as we rise slowly from the depths, leaving behind the silence and the glow, the pressure and the patience, we carry those lessons with us. We carry the knowledge that life is more resilient, more inventive, and more extraordinary than we ever believed. We carry the understanding that the boundaries of the possible are far wider than we once thought. And we carry the awareness that the deep is not just a place on a map. It is a reminder, a quiet, persistent voice, that the universe is vast and alive, and that we're only beginning to listen. Even now, as we break back into the light, the deep is still speaking. Its currents still move, its creatures still drift and hunt and glow. Its slow pulse still beats beneath the surface of the world. It is still there, waiting for us to return, not to conquer or to claim, but to listen once more. And maybe, as we listen, we will hear not just the story of the deep, but the story of life itself, told in the language of darkness, pressure, patience, and endless possibility.